This is Chapter 9 from the Electrician program. This is grounding. Some of the objectives for this chapter are to cite working principles for electrical grounding, explain equipment grounding and the methods used to install it, explain how system grounding works, define bonding and explain how it is done, explain the operation of ground fault circuit interrupter or GFCI and where it is used, know which branch circuit require an arc circuit interrupter, and to understand how AFCI works and the hazards it is designed to prevent. Some of the technical terms used are arc fault circuit interrupter, AFCI, bonding, equipment grounding, ground fault circuit interrupter, GFCI, grounding, and system grounding. Grounding refers to the connection of all parts of a wiring installation to the earth or to other systems that are connected conductively to the earth. This deliberate connecting of the system and the earth provides for the safety and protection of the system itself and the people installing it, testing it, or using the system. Grounding basics. Grounding protects by limiting the possibility of damage to electrical equipment and conductors and by preventing shock to persons contacting electrical equipment. Electrical systems could receive extremely high voltage from several sources. One of them is lightning striking electrical wiring or service wiring, figure 9-1. Insulation breaking down in the transformer and allowing high voltages. Accidental contact between the service conductors and high tension wires. In any of these mishaps, very high voltages could enter the electrical system. Voltage could be in excess of several thousand volts. In a system designed to carry no more than several hundred volts, the damage would be substantial. Without proper grounding, the high current related to the high voltage would create so much heat that conductor insulation would melt. Surrounding structural materials could ignite and burn. With a system properly grounded, this excess voltage and current is directed to earth rapidly. The excess should travel through the grounding conductor and not affect the electrical system at all. For this, see figure 9. In the previous chapter, we learned about the dangers of short circuits and ground faults. In either case, without proper grounding, an unwanted electric current could be induced in the system over its exposed portions. Proper equipment grounding would carry this unwanted current back to the device or back to the service panel. Again, proper equipment grounding would carry this unwanted current back to the service panel, where it would cause the OCPD, overcurrent protection device, to open the circuit. Excess currents would go to ground. For this, see figure 9-. There are basically two kinds of grounding for electrical wiring. One is system grounding and the other is equipment grounding. They have different purposes and involve two different electrical paths. System grounding. System grounding is the intentional connection of one conductor of the electrical system to earth. This ground connection is usually to the neutral conductor if one is available in the system. However, it can be a line conductor, as in a three-phase, three-wire delta system or a two-wire 120 volt single-phase system. The neutral or line conductor selected to be grounded is connected to a grounding electrode. This may be a driven rod or a driven ground rod that reaches at least 8 foot deep into the ground for contact with moist earth. A metallic water piping system of 10 feet or more in length. A buried ground plate. Other grounding means are outlined in the section 250.52a of the National Electric Code. For this, figure 9-4. Any of these methods can be used to ground the system. A combination of methods is also acceptable, and in some instances it is desirable. Proper grounding of electrical systems is required to 1. Limit the voltage entering the system from surges in power from the supply transformer or from lightning, or 2. Hold all parts of the electrical system, including non-current carrying enclosures, at 0 potential to ground. The grounded conductor, neutral or white wire, forms an unbroken path from all the various circuits to the service entrance panel. All the neutral conductors meet in the service panel and connect to a common bus bar called the neutral bus. The neutral bus bar is connected to the ground bus by the main bonding jumper. The ground bus is connected to the grounding electrode by the grounding electrode conductor. Should overcurrent accidentally reach the system, it will be drained off harmlessly into the ground before it can be damaged or before it can damage any part of the system. The grounded conductor should never have its continuity interrupted by switches, fuses, or circuit breakers. This would cancel its value as a path to ground. Devices that interrupt the circuits can be used only on hot wires, ungrounded conductors. The grounding of the neutral wire is done at both the building's service panel and at the power supply pole. For this, see figure 9. A commonly accepted method of system grounding is to connect the neutral conductor to one or more ground rods. The rods must be driven into a depth of at least 8 foot. The depth is important as the rods must be in contact with moist earth for good grounding. When multiple rods are used, they should be spaced at a minimum of 6 foot apart. Ground rods are one of many types of grounding electrodes. They are connected to the ground by a stranded copper conductor no smaller than 8 AWG. This bare wire is known as the grounding electrode conductor, or GEC. Looking at figure 9-6 at the bottom of the screen, you can see proper sizing of the grounding electrode conductor. Another method of system grounding is to connect the grounding bus to the metal piping of the water supply system in the building. It is a common practice and required to use both grounding methods together. It is a common practice and requirement to use both grounding methods together. It is necessary that the two grounds be interconnected or bonded. Bonding. Bonding means joining all metal parts of the wiring system, like boxes, cabinets, enclosures, and conduits, together. Bonding ensures having good continuous metallic connections throughout. Referred to Article 100 of the National Electric Code, bonding is required at all conduit connections at the electrical service equipment. Points where a non-conducting substance is used that might impair continuity, that is, where current may not be able to flow past the non-conductor. Such bonding is done by connecting a jumper around the conducting substance. At all service equipment enclosures, whether inside or outside of the building, and all metallic components of the electrical system that normally carry no current. If a grounding electrode conductor is properly bonded to the metal service equipment, a fault between an ungrounded conductor and any grounded equipment will follow a low resistance path to the grounding conductor at the transformer. This would allow the OCPD to open the circuit rapidly. Circuits having conductors enclosed in non-metallic sheaths or plastic conduit must have an additional grounding wire. This wire must be interconnected between the outlets. Figure 9-7, top of the screen, indicates the size of the grounding wire. This wire ensures a continuous equipment ground. When metal conduit is used, the conduit itself is the grounding means. If the conduit provides an uninterrupted path back to the service entrance. If it does not, an additional equipment grounding conductor must be run in the conduits. For this, see figure 9-8, bottom of the screen. How the system ground works. Article 250 of the NEC deals with grounding details and should be understood by anyone intending to do electrical work. In fact, a thorough understanding of both system grounding and equipment grounding is essential to completing an electrical installation that is safe to both persons and property. This is the foundation or the fundamental basis for the creation of the NEC. Equipment grounding. Equipment grounding is the method that bonds the equipment grounding conductor to equipment enclosures and metallic non-current carrying equipment. Figure 9-9. A permanent and unbroken path is formed back to the service neutral and the grounding electrode. If a system does not have a grounded conductor or neutral, one of the line or phase conductors may intentionally be grounded or may be intentionally grounded. This is common when there is a three-phase, three-wire delta system or a two-wire 120-volt single-phase system. One conductor of the system is grounded by connecting it to the grounding electrode. The equipment's ground protects the electrical equipment from damage should a live conductor make contact with the equipment housing or frame. This is known as ground fault. It occurs when conductor insulation fails or when a wire comes loose from its terminal point. Not only is this damaging to the electrical equipment, but it exposes the equipment user to the danger of shock. For this reason, all metal electrical enclosures, frames, wireways, and conduits must have a good ground continuity. The relationship between the system ground and the equipment ground is shown in figure 9-10. Ground fault circuit interrupters, or GFCIs. The importance of a good grounding system in electrical wiring cannot be overemphasized. However, in certain situations, good grounding is not enough. Too many individuals have lost their lives from improperly maintained or imperfect grounding or electrical equipment. Such situations exist whenever defective, worn, or misused equipment is handled by the operator, especially in damp or wet areas. A ground fault circuit interrupter, or GFCI, is a device that opens a circuit if an unusually large current to ground is detected. Having this device in the circuit is a way of preventing shock hazards when a poorly grounded equipment is operated. For this reason, the NEC requires GFCI protected circuits at the following locations. Must be in readily accessible locations, receptacles in bathrooms and outdoors where there is direct grade access, including bathrooms, in motel guest rooms, unfinished basement receptacles, all kitchen countertop receptacles, crawl spaces if at grade or below grade, wet bar sinks, all receptacles in garages, and receptacles that are not part of permanent wiring, such as those used for temporary power during construction. Requirements may be met by installing GFCI breakers or receptacles on the circuits. For this, see 9-11. See section 210.8 for more details. GFCIs open the circuits if a current leakage or fault to ground exceeds 0.006 amps or 6 milliamps. Note that a person can be electrocuted by a current of only 2 milliamps. Normally, the current going to the appliance along the ungrounded wire, and the current returning to the source along the white or grounded neutral conductor are equal. See figure 9-12. During a ground fault or short circuits, however, an imbalance occurs and the difference represents a dangerous shock hazard. A GFCI monitoring the circuit will sense an imbalance, or will sense any imbalance greater than 6 milliamps, and will immediately open these circuits, stopping the dangerous current flow. Arc Circuits Interrupter, or AFCI. The NEC requires that any 125 volts, 15 amp, or 20 amp branch circuit that supplies outlet receptacles that are not GFCI must be protected by a listed arc fault circuit interrupter, or AFCI. The AFCI opens the circuit when an arc fault is detected. By detecting arc faults, AFCIs will help prevent fires from starting. The breaker form of the AFCI is similar in appearance to a GFCI breaker. See figure 9-13. The AFCI detects arcing faults that are not detected by standard breakers or GFCIs. Typical conditions that may generate arc faults include the following: damaged wires, frayed conductor insulation, loose electrical connections, overheated or otherwise stressed electrical cords, and damaged electrical appliances. Moving on to the review questions. Number 1, true or false? Grounding is designed to protect people and not equipment. That is false. It is designed to protect both. Number 2, a ground rod must be at least 8 foot long to make good contact with earth. Number 3, true or false? A neutral wire can have a switch attached to it. That is false. Must provide a continuous path to earth, ground. Number 4, true or false? If a system is grounded, it does not need to be bonded. That is false. That is false. All system components should be bonded to ground as long as they are conducting or metal. A CFGI breaker or receptacle will open a circuit where there is a current leakage to a ground fault greater than 6 milliamps. 6. List 3 locations where GFCIs are required, and these are damp and wet areas, kitchens, crawl spaces, garages, and unfinished basements. 7. All circuits that are not protected with a GFCI must be protected by an arc fault circuit interrupter or AFCI. 8. True or false? In general, GFCIs prevent a shock hazard and AFCIs prevent fires, and that is true in general. Know the code. Number 1, Article 250 contains most of the information about grounding and bonding. This is page 70-103 on the 2017 NEC. Where does 210.8A1 require GFCI protection? And the answer is bathrooms. 3. Which section of Article 210 covers arc fault circuit interrupter protection? And that is 210.12, page 70-60, 2017 NEC. And that wraps up this chapter, chapter 9, grounding and bonding.